Learning Objective 7 is about the outer and inner hair cells. Now there are inner hair cells and outer hair cells. They're all hair cells, but they are arranged in different sorts of layers. The inner hair cell is the ones depicted here on this kind of dark green color. The inner hair cells are the primary source of auditory information. So when we have stereocilia deflection and the release of neurotransmitter and all of that, that occurs at the inner hair cell that goes on towards the auditory system. However, there are additional hair cells called outer hair cells, and they are arranged in a row-like pattern, and there are 3 rows. Now, the outer hair cells act essentially as an amplifier. They receive the kind of first wave of movement and the pressure differential induced by the basilar membrane deflection. And then that signal is essentially amplified by the outer hair cells such that you can have a better input upon the inner hair cells to drive that primary source of auditory information. This table compares and contrasts the function, arrangement, synapse connections, and efferent activity or efferent innervation of the inner versus the outer hair cells. Now, as I mentioned previously, the inner hair cells are the primary source of auditory information, and the outer hair cells are the primary cells that amplify the sound waves in order for the inner hair cell to transmit that information. But the outer hair cells are specifically also contractile. So you probably didn't realize this, but epithelial cells can contract, kind of like a muscle. And these cells, because they are this specialized epithelial cell, they are also contractile. They have contractile proteins within them that upon their kind of activation, essentially contract and squeeze the cell in and out. This is what makes the mechanical vibrations of the basilar membrane amplified, because it's essentially sensing sound and then they contract and then kind of boost the basilar membrane deflection just a little bit more, and that is how it acts as an amplifier. Now arrangements are different. There are a single row of inner hair cells, but there are 3 rows in the outer hair cells. The synapses will synapse on the inner hair cell side with a terminal of the primary afferent sensory neuron, and they do so with primary afferent neurons from off of the spiral ganglion in the outer hair cells. So very similar kind of arrangement there. Efferent activity is also similar but with different purposes. An efferent neuron can synapse upon the inner hair cell and modulate its activity up and down. And then the same thing with the outer hair cells. An efferent neuron can synapse with the terminals on the outer hair cells to change its properties, and we're going to talk about that next. I mentioned previously that the outer hair cells are contractile, but they don't just spontaneously contract, although they can. The purpose is to be contractile for a variety of reasons. So because the motility of the outer hair cells, because they are mobile, they're contractile, if in theory, because they cause that basilar membrane to move, and that's what amplifies the signal, it is conceivable anyway that the motion induced onto the basilar membrane by contracting outer hair cell could be backwards, essentially toward the oval window, out through the middle ears, move the ossicles, and then cause kind of an internal displacement of the eardrum. And that can result in a process called the ear itself producing a sound. And this in fact actually happens. And it's usually pure tones, but it can also be kind of pulse-like sounds as well. And sometimes it can be so loud that you can hear it coming from somebody sitting next to you. And a lot of times you don't even know that it's happening. So if you ever hear these strange little tones, it could be coming from the olivocochlear efferents acting upon outer hair cells, causing them to contract and essentially causing a sound wave to move out of the ear. rather than into the ear. The impulses that originate from these olivocochlear efferents originate from the superior olivary complex, which is why it's called olivo. It arises from the olivary complex, particularly the superior olivary complex, and goes to the cochlea. So that's why it's called olivocochlear efferents. And then the medial branches of that complex innervate outer hair cells, and the lateral branches innervate inner hair cells. And the reason why I bring this up is because this is the basis of some hearing tests that measure what we call autoacoustic emissions. Now, this is done in children and other sorts of hearing deficit individuals, not only in children, but also in newborns. Now, I knew that this was a phenomenon that can be done on newborns, and so this is a picture down here of a newborn getting an autoacoustic emission test. They're routinely done on infants just to test the function of their inner and middle ears, just to essentially show that they are in fact working. And I knew that this was a phenomenon, and I was so excited to see this test done on my son after he was born. I wanted to watch it and see what it looked like and really be involved. And I had gone out of the room for just a minute, and the audiologist came in and did the test, and I missed it. And I was so disappointed that I missed this because I thought it was so cool and I was finally going to see it in person. But regardless, his hearing was fine, so we had some good news there. But again, this is something that actually happens, and they test all newborns with this. They also use it in tests of tinnitus or tinnitus and other ototoxic hearing deficits. Now, autoacoustic emissions are essentially that sound that's produced by the ear as arriving from those olivocochlear efferents. Usually it's inaudible, although it's such a low intensity, usually you can't hear it. However, sometimes it can be loud enough that you can hear it from another person. I've never personally heard it, or at least if I did, then I didn't know that that's what I was hearing. But I have read that you can in fact hear it sometimes. There are two types. The spontaneous ones, which are that just kind of spontaneous emission, the spontaneous sound, and that actually occurs in a lot of people in just normal hearing physiology. And there's also evoked. Evoked autoacoustic emissions are what's done in this test. They have a sound from this device. It travels through the wire, and they put a little recorder, a little instrument here, just pressed kind of against the external acoustic meatus, or the external auditory meatus, and they pulse a sound into the ear. And that little tone will then result in a almost reflexive response of the autoacoustic emission coming back out of the ear. And that is why we call it evoked. Again, they're usually pure tones or clicks. And we believe that they are generated from the outer hair cells specifically contracting, causing movement in that basilar membrane, which then induces a sound wave that originates from the basilar membrane and then comes out of the ear. Learning Objective 8 is about brain processing of auditory input. Similar to the somatosensory and visual systems, the auditory system likewise has a primary and secondary auditory cortex. The first one is A1, or the primary auditory cortex. Similar to the other primary sensory cortices, this one, while essential in the perception of sound, is really more about the highest order processing of sound from a more crude perspective. So this is more about loudness, volume, rates of frequency, things like that, compared to more higher level executive processing of sound, which is what the secondary auditory cortex does. And that's what we're going to look at next. The primary auditory cortex is very close to the secondary auditory cortex. The secondary auditory cortex anatomically is composed of multiple areas that I'm not going to go into, but functionally I do want to emphasize is that it responds and processes much more complex sounds than the crude noise being processed by the primary cortex. So these are things like music or sounds, speech, inflections, identification of sounds, naming things. Compared to the primary auditory cortex, the secondary auditory cortex is less organized in terms of what we call tonotopic arrangement. Tonotopic arrangement is kind of like the homunculus in the somatosensory system, where proportionally input from different parts of the bodies maintain that same relative organization all the way up to the sensory cortex. Well, similar to input from various levels of the basilar membrane, all the way through the cochlea, all the way to the primary auditory cortex, that relative proportional organization remains. However, that organization becomes a little bit more disorganized, if you will, by the time that information gets to the secondary auditory cortex. And this disorganization is probably correlative with the complexity of sound processing that takes place there. This summary table compares and contrasts the auditory cortices with their functions. Learning Objective 9 is about efferent innervation of the auditory system. We've spent a lot of time talking about the physiology of the sensory component of the auditory system, and we've previewed a little bit, particularly in regard to olivocochlear efferents, about the efferent innervation of the auditory system. But we're going to go into more detail now of the olivocochlear efferents, also the motor neurons that innervate the middle ear muscle structure, and then the autonomic innervation of the inner ear, and why all of these work together to promote hearing senses. First up are the olivocochlear efferents again. So now that you have learned about the superior olivary complex and its location and afferent function, here it is again in terms of being the nucleus of origin for an olivocochlear efferents. These olivocochlear efferents being efferent in that their cell bodies are located in the lateral or the medial superior olivocochlear complex, and their branches or their terminals are going to come out and then innervate either the inner hair cells or the outer hair cells. There's a little bit of a nuance and difference in the way that they do so. The outer hair cells are directly innervated by these branches, and that is part of their contractile motor function, because if there are contractile elements here and then they were to contract, then contraction here would pull this structure closer together and it would then contract, and that is the source of those autoacoustic emissions we talked about. Nuance, I'm not going to test you on these different nuances, but you can note here that the inner hair cells don't necessarily get a direct synapse onto the epithelial cell itself. It's actually contacting the afferent that is coming away from it at this location right here. Okay, so this is kind of busy now, so let me go and delete some of this input here. Okay, so we can see it there. The purpose of these are for the outer hair cells in response to very loud noises, so loud that it might damage the hair cell. It can decrease basilar membrane motion. Okay, so there's two functions. One, it can contract these outer hair cells, and if it does so, it would contract and essentially pull at the basilar membrane and induce a wave of sound exiting the ear. But here, this is serving to dampen the motion, essentially kind of freezing these hair cell contractile properties, if you will, and keeping the basilar membrane stiff and unmoving. And that is serving a purpose to help dampen very loud, very dangerous sound waves that might be coming in that would otherwise harm those delicate hair cells. Therefore, we say it decreases basilar membrane motion and reduces responses of the inner hair cells in the auditory nerve fibers to loud inputs, very intense loud inputs. This is serving to protect hair cells from damage due to intense sounds. And this is a distinct function that differs from the autoacoustic emissions we talked about earlier on. Next, we have middle ear efferents. These are motor innervation to the muscles of the inner ear, like the tensor tympani, and also to the stapedius, and essentially is serving to attenuate sound. Again, this is bilateral response to very intense high levels of sound that might damage hair cells, and essentially is tensing or constricting those muscles to keep the ossicles like the malleus and stapes from moving, which if you can kind of dampen the vibrations of those inner ear bones, then that is serving to attenuate a little bit of the sound that might otherwise reach the hair cells and damage them. They can act at low and high frequencies. It's serving to prevent damage, and that's kind of their function in terms of every day-to-day type of work. It's thought that their working at low frequencies helps to mask very, very low frequency sounds so that you can really discern or discriminate the nuances of human speech. But in addition, it is also protective of the inner hair cells from intense sounds, or the outer hair cells. Middle ear efferents are also implicated in tinnitus, which is a constant ringing in the ear. And finally, we have autonomic innervation to the ear structures. They can arise from the eighth cranial nerve. It can arise from the carotid-tympanic nerve, which is autonomic off of the superior cervical ganglion. That, of course, is a sympathetic autonomic innervation resource. These will innervate the mucous glands of the tympanic membrane and the blood vessels of the ear and the eardrum. So that could, of course, regulate the vascular tone of those blood vessels. It can improve the mucus secretions in this area. And then, of course, if you have acoustic nerve supply providing sympathetic regulation, that can monitor the vascular tone in terms of the blood to the cochlea, all of which can impact hearing. And again, these autonomic innervations are comprised of sympathetic adrenergic fibers. Finally, food for thought. Just a quick question. I'm not going to answer this today, and I'm not going to ask any test questions or anything about it. But when you think about osteopathic manipulative medicine, how can that impact sympathetic tone in general in the body? And is that possible then that you can impact vascular tone, other sorts of innervation to the special senses? Just a food for thought.